Hi everyone, it has been a while since I last posted a video. Let me hope all of you are doing fine wherever you are. It's really hard time. Everybody is battling COVID-19. It has crippled the economies all over the world and it has sent students out of school. But let me hope you are all doing fine. Okay, let us do some online teaching today. I want to teach you some curriculars. When we talk about curriculars, there are basically two areas of emphasis. There is differential curriculars, and then there is the integral curriculars. So today, we want to talk about integration. We want to talk about integration. What is integration? And what does it deal with? That's what we want to discuss today. Okay. So we are saying that integration is the reverse process of differentiation. Yes, that's true. When we are differentiating a function, or in differentiation, we start with a function and then go ahead to find the derivative or the differential coefficient. Okay? But in integration, we're gonna start with the differential coefficient and then work back to trace the function that was differentiated. So that backward process of tracing the function which was differentiated is what we call integration. Okay, let's look at this example to understand the point. So if one is given a function y is equal to x cubed plus bx plus f4, that is a quadratic equation, and you want to get the derivative of this function, what you do, you differentiate both sides with respect to x. The y is equal to d by dx of x cubed plus 3x plus 4. Okay, and when you go ahead and differentiate, you're going to get dy by dx giving us 3x squared plus 3, simply because when differentiating 4 is a constant, differentiating a 4 you get 0. Now this process of starting with a function here, and then from the function you move and get what we call the differential coefficient, is what we call differentiation. Now in integration, what they will simply do to you, they will give you a function. They will give you this function which is 3x squared plus 3. Okay, and they want you to work back and trace this function which is x cubed plus 3x plus 4. Now that process of working backwards, you start with a differential coefficient and end up with a function that was differentiated, is what we call integration, and that's what we want to discuss today. Okay, we have seen that integration is the reverse process of differentiation. Okay, so we want to see how do we work backwards and trace functions that were differentiated if we start with the derivative this time. We know that when you differentiate x power 4 plus 2x, you end up with a 4x cubed plus a 2. Okay, so I can start, therefore the integral of 4x cubed plus 2 with respect to x is x power 4 plus 2x. Simply, we are defining integration as a reverse process. This example is just emphasizing that you are going to start with a derived function and then trace the function that was differentiated. That's what we call integration. Okay, so if you cannot do integration if you don't have enough knowledge of differentiation, that's the prerequisite knowledge for each of you who are attending and listening to me. Okay, for you to be able to understand integration, you must have a very strong background of differentiation. Actually, you should have understood all the differentiation. That's what I'm trying to say. Before we go into the details of integration, let's get to understand what we call the integral notation. Okay. Integral notation. How do we represent integration? By symbol? Okay, so that one is able to tell that this, what they want me to do is to go ahead and integrate. Integration is denoted by the symbol. Okay, which is an elongated S. Elongated S for sum. When we perform the integration process, actually we are summing functions, but in this case, we sum continuous functions. So we sum continuous functions. For example, if one is asked to find the distance the tire of a bicycle, sweeps of a given distance, you cannot sum it like a 1 plus 2 plus 3. No, the summation is a continuous function. So that's what we talk about in calculus. That's why we are studying calculus. Integration is a summation. So we use that long S to stand for a summation of a continuous function. Okay, so how do we denote it? We have seen it is represented by a long S. And how do we write this? So we write integral dx to mean integration of whatever in the bracket with respect to x. So when we are writing, okay, we are going to perform the integral process. It is this combination. These two move together. Okay, it is this part. Okay, and that part. The two move together. The integral of whatever you have here with respect to x. This is a single part. You insert a function in this operation, and then it outputs some function. Okay, so that's how we write the integration. Okay, or the integral symbol is written as a long S, but it moves with respect to x to mean that you are going to integrate a function with respect to x. Now, this is a warning before we move on. Don't think that we only integrate with respect to x. Some functions are defined in terms of y. So if a function is defined in terms of y, then you're going to integrate that function, whatever function you have here, with respect to y. If a function is defined in terms of z, then you integrate whatever the function is with respect to z. So don't think that we only integrate with respect to x. It is just that, many people love x, and x appears to be so common. So in most teachings, the variable which is selected, okay, it is the most favorite, some kind of variable letter in the alphabet to mathematicians. So, but don't think that we only integrate with respect to x. We can integrate with respect to y. We can integrate with respect to z. We can integrate with respect to any variable. Okay, so it should not be crammed that integration is always with respect to x. No, that's not true. So when we perform the integral process, we always add a constant of integration if we are integrating indefinitely. Okay, integrating indefinitely means that the integral is not carried out within a particular limits. Okay, if the integral is not having limits, we don't have limits of integration, that is an indefinite integral. So we always add a constant of integration. But before I emphasize addition of a constant of integration, we must get to understand what is this constant of integration we are talking about. Everybody must really be able to understand this. This is simple knowledge, but most people have, because of the negativity there. I think it is some kind of inherited negativity of the subject. So when you talk about constant of integration, guys start scratching their heads and they think it's maybe something so complicated. Okay, this is as easy as eating an orange. Okay, so what is a constant of integration? Let's consider the three derivatives. Okay, look at d by dx of x cubed. Okay, you end up with 3x squared. Then d by dx of x cubed plus a 4. Still it will give us 3x squared. What about d by dx of x cubed minus a 2? Still the derivative will be 3x squared. Now here we can say that the integral of 3x squared with respect to x, you are tracing what was differentiated, and therefore what was differentiated is x cubed. Then someone can say here that, okay, I'm seeing the function that was differentiated, so when I integrate 3x squared with respect to x, I will be getting x cubed plus a 4, because on the left hand side you are seeing a function that was differentiated, and here when you are trying to trace that function, it's just easy. Okay, and here the last example, this last part, if you integrate 3x squared, okay, then with respect to x, it will take you to x cubed minus a 2. Now, what if we didn't have knowledge about what was differentiated, and we are just told to integrate? Okay, suppose somebody just says, okay, you integrate 3x squared without that kind of history. How are you going to go about this? We are very sure the integral of 3x squared is x cubed, but in this case we are going to add a constant c. Okay, c is called the constant of integration. It caters for whatever disappeared. Okay, when in the process of differentiation, whatever went to 0 or disappeared, whatever constant disappeared in the process of differentiation, when we integrate, we represent it by c. If we have more information about the function in the question given to us, we can go ahead and trace c. But if we don't have any knowledge about the value of c, just leave it as an arbitrary constant. Okay, so always add a constant of integration whenever you are integrating indefinitely, or whenever you integrate without limits of integration. So secret has what disappeared in the process of differentiation. All right, hope this point is understood. So we want to talk about integrating powers of x. Okay, we want to integrate powers of x. So when that y by dx is equal to x to the n, then the integral of x to power n by dx will be equal to x to power n plus 1 over n plus 1, okay, provided n is not equal to minus 1. When n is equal to minus 1, this is a different story. So when you are integrating powers of x, okay, so here we are integrating n belongs to a set, okay, of the rationals. It is a rational number. It could be -2, -3, it could be a half. As long as it is not -1, the rule for integrating powers of x, increase the power by 1, divide by the new power, okay? That is it. That is all what we need, okay? This is a rule that we shall be following whenever we are integrating powers of x. So to integrate a power of x, as long as that power of x not -1, increase the power by 1 and divide by the new power. So let's just work out a few examples, okay? Examples. Integrate with respect to x. A, they want us to integrate 1 over x cubed. Okay, then B, they want us to integrate x to the -4. Okay, C, 2 over x squared. Then D, x to power 1 over 2. So we want to just practice with this issue so that you get to master how to integrate powers of x. You know, we are doing all this because at some point we're gonna sum up everything when we start now dealing with complicated integrals. So we begin with these individual parts and then bring them together and we'll solve bigger problems. So let's begin with it. Something one can despise is one who would say, why are we learning this? But let's get used to this after we have mastered integrating powers of x. Now we go ahead and solve more complicated problems. So this is very simple. Let's look at the solutions. Okay. First one, they want you to integrate. It is 1 over x cubed by dx. Write this as, use knowledge of indices and write this as x to the -3 by dx. Remember the rule of integration is increase the power by 1, divide by the new power. So -3 plus a 1 over -3 plus a 1. This is the same thing as, you know, integrating 1 over a -2x squared plus a constant of integration. Okay, that's A. B. B, they want you to integrate x to the -4 by dx. This more is like the first one, just integral of x. Why do we repeat ourselves at this stage? Let's just write the answer. Okay, and we say this is x to the -4 plus a 1 over -4 plus a 1, which is x to the -3 over -3, but x to the -3 using knowledge of indices is 1 over -3 x cubed plus a constant of integration. Okay, C, they want you to integrate C. We have to integrate it 2 over x squared by dx. So first write, always organize your information. Okay, we have been dealing with x to the n, but now this is 2 over x squared. This is going to be 2 x to the minus 2 by dx. Okay, and this is equal to a 2 is it is a constant term which can factor out, and then you integrate x to the minus 2, okay, by dx. So we end up with 2x negative 2 plus 1 over minus 2 plus 1. And if you go ahead and do the mathematics, this is going to be 2, okay, a minus 2 over x plus a constant of integration. Please, this is a warning. So many students, because they're excited about integration, they think that this is going to be, okay, I will cross it out. This is not 2 over x, 2 plus 2, 2 plus 1 rather, over 2 plus 1. And you end up with the 2 over x, okay, 2 times 3 over x cubed. That is not equal to, okay? Do not make a mistake. Remember, we are integrating x to power n by dx, and not, okay, integral of 1 over x to the n. So if they give you this integral, always write it as x to power n before you go ahead to integrate. Okay, so many will make that mistake and they will end up failing. This is not true. I'm crossing it out. Okay, so after learning how to integrate powers of x, we want to integrate polynomial functions. Now, polynomial functions are integrated term by term with the individual constants of integration consolidated into a single constant c. Okay, so what does this mean? Let's get to the meaning of this by looking at this example. If you're given a polynomial function, which is integrate x to power 5 plus 4x cubed minus 2x squared plus x minus 3 with respect to x. Okay, so what they are meaning, this just for explanation purposes, don't do it, but I will do it just to explain to you. They are meaning that you integrate x to the 5 by dx plus integrate 4x cubed by dx, okay, minus integrate 2x squared by dx, then plus integrate x by dx minus integral of 3 by dx. That's the meaning of this statement. Polynomial function is integrated term by term. You look at a term, integrate it. Okay, so what will you get when you integrate this? This will be x to power 6 over 6 plus a constant c1. Then add it to 4x power 4. This is going to be 4x to power 4 over 4 plus c2 minus 2x cubed over 3 plus c3 plus x, okay, squared over 2 plus c4 minus 3x, okay, plus c5. That's the meaning of the individual constants. Okay, when you integrate a term, it will come up with a constant. Next term also come up with a constant, okay? But we don't do it like this, no. I'm just doing this to explain to you. Now, this constant here, okay, assuming that was maybe a 2, and maybe this is a 3, maybe this is another constant, which is a minus, whatever. They are all constants. These constants, okay, add up together into a single constant. So instead of adding individual constants to each term after integrating it, we integrate the terms, and then at the end of it, we add a single constant c. Let me hope this point is understood. We are integrating polynomial functions, and I'll give one or two examples, because integrating polynomial functions is the same thing as integrating powers of x. So there is nothing new here. So when you go ahead and do the math, this is what you end up with. It produces this integral at the end of it, okay? Those individual constants are consolidated into a single constant c, and then that is it. We have integrated the polynomial function. It's not a big deal, okay? So next, let me just give you one example to try out on your own. Before I give you the example, there's something I want to emphasize to somebody learning or seeing integration for the first time, okay? I have integrated the 3 and end up with 3x, but how do we come up with this result? Remember, a constant, okay, has a silent variable to power 0, because a number to power 0 is 1, so 3 times 1 is 3. But now, since the rule of integration tells us that we have to add the power, okay, we add to the power, we add 1 and divide by the new power. This is going to be 3x 0 plus 1 over 0 plus 1, and you end up with 3x, okay? That's why when I integrated the 3 here, a minus 3, I ended up with this as 3x, okay? You have to understand, okay? When it is a constant, if I was given something like 3x to the power maybe a half, the 3 here is not affected, because this will be looked at as by dx, of course. This will be looked at 3 times the integral of x to power half by dx, okay? And this will be 3 times, it's going to be 2 over 3 of x to power 3 over 2, okay? So you have to understand, but when you are given maybe to integrate 5 by dx, look at this as the integral of 5x to power 0 by dx. Then now you can say it is a 5. Go ahead and integrate x to power 0 by dx, and you end up with 5x. So I wanted to just emphasize something about the constants, how to integrate constants. This is how we deal with the constants. So these two are your questions to try out to test your understanding. But before we end our discussion today, let's end it with the limits of integration. Okay. So to understand this, let the integral of a function of x by dx, okay, let's assume after integrating, we end up with a function which I'm calling capital F of x, okay, plus a constant. Now, if to integrate within given limits, that means that the x values are stated. You start with the value maybe a, and end and move up to the value b. You are integrating f of x by dx, okay? This will be f of x, or no, it's going to be f of upper limit, which is a b, plus or c minus f of A plus C. So if you open the bracket, you end up with f of B minus f of A. The constant of integration cancels out when you are feeding in the limits after integration. Okay, lower limit is subtracted from the upper limit. You feed the limits in the function you obtain after integrating. Okay, for example, if I integrate from 0 to a particular value, maybe 2, and I'm integrating the function which is x squared by dx. Okay, this is going to be x to power 3 over 3. Okay, and I normally use these square brackets. Okay, so that I'm moving from 0 to 3. So we substitute a 3 first. Okay, 3 to power 3 divided by 3 minus 3 to power 0 divided by 3. The answer will be a 9. Okay, so the constant disappears when you feed in the limits of integration. Now, ladies and gentlemen, our discussion today ends here. Tomorrow we are going to move, talk more about integration, and we want to first talk about integrating sine and cosine. Then after, we talk about the exponential functions, and now we start bringing in some more complicated functions integration. When we have these small parts catered for, it will always be easy for us to understand, something in large quantity. Okay, so if we may have a mixture of functions, e to power x times cosine, how do you go about that? Okay, you cannot understand that unless you know how to integrate these small functions. So I prefer to begin with the small functions, then I start now adding them up. Okay, I bring function of a function and so many things, so many parts of integration. It's just interesting. Let's wait for tomorrow. Our discussion today ends here. Okay, let's wait for tomorrow and discuss, something more about integration. I wish you a safe day.